Based on the incident description, it is likely that the tie wire caused a face-to-face fault within the torque bolt joint area of the bus duct. This fault would have created an intense short-circuit current, resulting in the blowing of the three 1600 amp fuses. While the external damage to the bus duct may be minimal, the internal damage caused by the intense short-circuit current could be significant. The arcing and heat generated during the fault could have damaged the conductive material, insulation, and other components within the joint area. It is prudent to order a replacement section for the affected portion of the bus duct as a precautionary measure. The damage to the joint area may not be immediately evident or discernible, but it could potentially lead to future problems, such as firstly, increased resistance and power loss, secondly, arcing and potential overheating, and thirdly, safety hazards to personnel. The replacement section should be installed by qualified electrical personnel who are familiar with the specific bus duct system and safety procedures. The following steps are typically involved in a bus duct replacement. 1. De-energize the bus duct. 2. Isolate the affected section by removing the bolts connecting it to the adjacent sections. 3. Cut and remove the damaged section. 4. Prepare the new section for installation by cleaning and lubricating the contacts. 5. Install the new section and tighten the bolts. And 6. Re-energize the bus duct and verify proper operation. While the bus duct may currently be operational after replacing the fuses, the potential damage caused by the fault warrants the replacement of the affected section. This proactive measure will mitigate potential safety hazards and ensure the reliable and efficient operation of the bus duct system. The introduction of a foreign object, in this case a piece of tie wire, into a bus duct system presents a significant risk of electrical faults. Bus ducts are designed with specific insulation and spacing to prevent unintended current paths. Any conductive material that bridges these gaps can create a short circuit. The location of the incident, near the torque bolt joint, is a critical area for maintaining electrical continuity and mechanical integrity. The fact that the security vendor was working in the electrical room and that the tie wire was present in a nearby basket highlights the importance of maintaining a clean and controlled environment in electrical spaces. Tools and materials should be carefully managed to prevent accidental introduction of foreign objects into electrical equipment. The resulting arc flash and burn injuries to the security vendor underscore the dangers associated with electrical faults. Arc flash events release tremendous energy in the form of heat, light, and pressure waves, posing severe hazards to personnel. The extent of the injuries, described as similar to sunburn, suggests that the vendor was fortunate to escape more serious harm. Proper personal protective equipment, or PPE, including arc-rated clothing, gloves, and face shields, is crucial for protecting workers from arc flash hazards. The blowing of the three 1600 amp fuses indicates a high-magnitude short-circuit current. Fuses are designed to interrupt overcurrents and protect equipment from damage. The fact that all three fuses blew simultaneously suggests a three-phase fault, where all three phases of the electrical system were involved in the short circuit. The replacement of the fuses allowed the bus duct to be re-energized, but it does not address the potential underlying damage caused by the fault. The U-shaped holes at the joint mentioned in the description are likely designed to facilitate bolting and mechanical connection of the bus duct sections. These openings, however, can also provide a pathway for foreign objects to enter the bus duct enclosure. The recommendation to replace the affected section of the bus duct is based on the principle of preventative maintenance. While the system may appear to be functioning normally after the fuse replacement, hidden damage to the insulation, conductors, or joint components could lead to future failures. Increased resistance at the joint caused by damaged conductors can result in localized heating and energy loss. This can further degrade the insulation and accelerate the deterioration of the joint. Arcing, even if not immediately apparent, can gradually erode the conductive material and create a carbonized path that promotes further tracking and flashover. A proactive replacement strategy minimizes the risk of future breakdowns, improves system reliability, and enhances safety. The replacement procedure should follow established safety protocols and industry best practices. De-energizing the bus duct is the first and most critical step. This ensures that workers are not exposed to live electrical conductors. Lockout-tagout procedures should be implemented to prevent accidental re-energization of the bus duct during the replacement process. Isolating the affected section involves disconnecting it from the adjacent sections by removing the connecting bolt. Care should be taken to support the bus duct sections during this process to prevent them from falling or shifting. Cutting and removing the damaged section may require specialized tools and techniques. The bus duct enclosure is typically made of metal, and the conductors are often insulated with epoxy or other high-strength materials. The new section of bus duct should be carefully inspected for any defects or damage before installation. The contacts should be cleaned and lubricated to ensure good electrical connection. The bolt should be tightened to the specified torque values to provide adequate mechanical strength and electrical conductivity. After the new section is installed, the bus duct should be re-energized and its operation verified. Voltage and current readings should be taken to ensure that the system is balanced and operating within normal parameters. A visual inspection should be performed to check for any signs of overheating or arcing. In addition to the replacement of the bus duct section, it is important to address the underlying causes of the incident. The presence of the tie wire in the electrical room suggests a need for improved housekeeping and tool control procedures. Electrical rooms should be kept clean and free of debris, and tools and materials should be stored in designated areas. Workers should be trained on the importance of preventing foreign objects from entering electrical equipment. Regular inspections of electrical equipment can help to identify potential problems before they lead to failures. Infrared thermography can be used to detect hotspots caused by increased resistance or loose connections. Ultrasonic testing can be used to detect internal arcing or corona discharge. These diagnostic techniques can provide valuable information for assessing the condition of electrical equipment and planning maintenance activities. The incident also highlights the importance of proper electrical safety training for all personnel who work in or around electrical equipment. Workers should be trained on the hazards associated with electricity, the proper use of personal protective equipment, and the procedures for responding to electrical emergencies. The National Electrical Code, or NEC, provides comprehensive requirements for the safe installation and maintenance of electrical systems. Article 368 of the NEC covers busways, including bus ducts. This article specifies requirements for the construction, installation, and protection of busways. It also includes requirements for the grounding and bonding of busways to ensure electrical safety. Section 110.16 of the NEC requires that electrical equipment be marked to warn qualified persons of potential arc flash hazards. This marking should include the nominal voltage of the equipment, the arc flash boundary, and the personal protective equipment required to work within the arc flash boundary. The arc flash boundary is the distance from the electrical equipment at which a person could receive a second-degree burn from an arc flash. The required personal protective equipment depends on the arc flash incident energy, which is a measure of the energy released during an arc flash event. The incident energy is typically calculated using an arc flash hazard analysis, which takes into account the voltage, current, and clearing time of the electrical system. The incident energy is expressed in calories per square centimeter, or cal per cm squared. The personal protective equipment required for different incident energy levels is specified in NFPA 70E, which is the standard for electrical safety in the workplace. NFPA 70E provides detailed guidance on the selection and use of personal protective equipment for electrical work. It also includes requirements for electrical safety training and work practices. The recommendation to replace the bus duct section is consistent with the principles of risk management. Risk management involves identifying, assessing, and controlling hazards. The potential damage to the bus duct caused by the short-circuit current represents a significant hazard. The risk associated with this hazard is the likelihood of a future failure that could result in a power outage, equipment damage, or personal injury. The replacement of the bus duct section reduces the likelihood of a future failure and therefore mitigates the risk. The cost of the replacement section should be weighed against the potential costs of a future failure. These costs could include lost production time, equipment repair or replacement, and potential liability for injuries. In many cases, the cost of preventative maintenance is significantly less than the cost of dealing with the failure. The decision to replace the bus duct section should be documented and justified. The documentation should include a description of the incident, an assessment of the damage, and a rationale for the replacement recommendation. The documentation should also include a record of the replacement procedure, including the date of the replacement, the name of the qualified electrical personnel who performed the replacement, and any relevant test results. This documentation can be used to track the performance of the electrical system and to identify any trends or patterns that may indicate potential problems. The incident with the bus duct serves as a reminder of the importance of electrical safety and preventative maintenance. By taking proactive steps to identify and address potential hazards, electrical system owners and operators can minimize the risk of failures and ensure the safe and reliable operation of their equipment. Regular inspections, proper training, and adherence to industry best practices are essential for maintaining a safe and efficient electrical system. The specific type of bus duct, a GE 2000 amp 480 volt system, indicates a robust design intended for significant power distribution. The 2000 amp rating signifies the continuous current carrying capacity of the bus duct, while the 480 volt rating specifies the operating voltage. The fact that the bus duct feeds emergency power underscores its critical role in maintaining essential services during power outages. Emergency power systems are designed to provide backup power to critical loads such as lighting, fire alarms, and life support equipment. The reliability of these systems is paramount to ensuring the safety and well-being of building occupants. The replacement of the bus duct section should be performed as quickly as possible to minimize the downtime of the emergency power system. Coordination with the building owner or operator is essential to schedule the replacement during a period of low demand. Temporary power may be required to maintain essential services during the replacement process. The use of a filler piece, only 4 feet long and fairly accessible, simplifies the replacement process. A filler piece is a short section of bus duct that is used to connect 2 longer sections. The accessibility of the filler piece makes it easier to remove and replace without having to disturb other parts of the bus duct system. The decision to order a replacement section for building stock is a prudent one. Having a spare section on hand can significantly reduce the downtime in the event of a future failure. This is particularly important for emergency power systems, where reliability is critical. The spare section should be stored in a dry and secure location to prevent damage. It should also be inspected periodically to ensure that it is in good condition. The long-term reliability and safety of the electrical system depend on a commitment to preventative maintenance and adherence to industry best practices.